Welcome back to the channel. Today, we're doing something different. We're going on a journey through AI history. Not the boring stuff. I'm talking about the 10 research papers that literally built everything you see today. ChatGPT started here. Self-driving cars started here. Every AI image generator, every chatbot, every recommendation system, they all trace back to these 10 breakthroughs. And here's what's wild. Some of these papers almost got rejected. Some were ignored for years, but each one changed everything. By the end of this video, you'll understand how we got from basic neural networks to AI that can pass the bar exam. Let's dive in. Let's start at the beginning. 1986, Rumelhart, Hinton, and Williams published a paper called Learning Representations by Backpropagating Errors. And honestly, this is the paper. This is the engine that runs everything. Here's why. Before this paper, nobody knew how to train neural networks with multiple layers. You had input, output, and that was it. But these researchers showed that you could train deep networks by propagating errors backward through the layers. Backpropagation. Think of it like this. Imagine teaching someone to shoot basketball free throws, but you can't tell them what they did wrong. You can only tell them the final score. That's what AI was before this paper. Backprop gave us a way to say, this layer messed up and here's by how much. Every single deep learning model today, GPT, Claude, DALL-E, AlphaGo, all of them use this algorithm. This paper is the foundation of foundations. Fast forward to 1998. Yann LeCun and his team publish a paper on something called LLMs 5, and this is where computer vision begins. Before this, if you wanted a computer to recognize handwritten digits, you'd write thousands of lines of code with rules. If there's a curve here and a line there, it's probably a 5. It was brittle, it was painful, and it didn't work very well. LeCun said, forget the rules. Let the network learn what a digit looks like. And he introduced convolutional neural networks, CNNs. These networks learn to see in layers. First layer, edges. Second layer, corners and curves. Third layer, complete shapes, just like your brain. This paper proved that neural networks could learn spatial hierarchies directly from pixels. No handcrafted features, just data and gradients. This is why your phone can recognize faces. This is why self-driving cars can see pedestrians. It all started with LLMs reading handwritten zip codes. Okay. Now we get to the Big Bang, 2012, ImageNet Challenge. This is the Olympics of computer vision. Identify objects in images, best accuracy wins. Traditional computer vision methods are dominating. Handcrafted features, support vector machines, years of careful engineering. Then, 3 researchers, Krzyzewski, Sutskever, and Hinton, show up with something called AlexNet. And they don't just win. They crush everyone. They cut the error rate almost in half, from 26% error to 15%. That's not an improvement. That's a revolution. How? 3 things. Deep CNNs with 8 layers. GPUs for parallel training. They used gaming graphics cards. And a massive dataset, 1.2 million images. Traditional methods couldn't scale. Deep learning could. This is the moment. After this paper, everyone pivoted to deep learning. Google, Facebook, Microsoft, billions of dollars started flowing into AI research. This is when deep learning went from academic curiosity to industry obsession. This paper changed everything. 2014, Ian Goodfellow has a revolutionary idea. And legend says he came up with it at a bar arguing with friends about generating images. Until this point, neural networks were classifiers. Show them a cat, they say cat. Show them a dog, they say dog. But Goodfellow asked, what if we could make networks create things? He invented generative adversarial networks, GANs. Here's the genius. 2 networks fighting each other. The generator tries to create fake images. The discriminator tries to detect fakes. They're locked in an arms race. As the generator gets better at faking, the discriminator gets better at detecting, which forces the generator to get even better. The result? Networks that can create photorealistic faces of people who don't exist. Art videos, voices. This paper launched generative AI. Deepfakes, stable diffusion, Midjourney, all descendants of GANs. Goodfellow basically invented AI creativity in one paper, written after drinks at a bar. Legendary. Same year, 2014, 3 researchers at Google solve a huge problem. How do you translate between languages with neural networks? The problem is this. I love AI in English becomes j'adore l'IA in French. Different lengths, different word orders, different grammar. How does a neural network handle that? Sutskever, Vinyals, and Lay introduced the encoder-decoder architecture. The encoder reads the English sentence and compresses it into a fixed representation. Basically, it captures the meaning. Then the decoder takes that meaning and generates the French sentence, word by word. This is the architecture that powered Google Translate's massive improvement in 2016. But more importantly, this paper showed that neural networks could handle variable length inputs and outputs. Translation, summarization, question answering. This architecture made it all possible. Before transformers came along and took over, this was how we did sequence modeling. 2016. Microsoft researchers face a paradox. Everyone knows deeper networks should work better. More layers means more learning capacity. But there's a problem. When networks get too deep, they become impossible to train. It's called the vanishing gradient problem. Remember backpropagation? As errors propagate backward through 50+ layers, they get smaller and smaller until they basically disappear. The early layers never learn anything. Ke-Ming He and his team solved this with an absurdly simple idea: skip connections. Instead of forcing every layer to learn from scratch, let information skip over layers. Let later layers directly access earlier layers. The result? ResNet, a network with 152 layers. Previous state-of-the-art was maybe 20, and it worked. Better accuracy, easier to train, more stable. ResNet became the default backbone for computer vision for half a decade. This paper proved that architecture matters. A clever design can overcome fundamental training problems. Skip connections are now everywhere in modern AI. March 2016, Seoul, South Korea. Lee Si-dal, one of the greatest Go players in history, sits down to play against DeepMind's AlphaGo. Everyone expects Lee Si-dal to win. Go is too complex, too intuitive. There are more possible board positions than atoms in the universe. AlphaGo wins 4-1. The world is stunned. The paper behind this is brilliant. DeepMind combined 2 techniques: deep learning to evaluate board positions and predict good moves, and Monte Carlo tree search to simulate thousands of possible futures. The deep neural networks provided intuition. The tree search provided calculation. But here's what matters. This was proof that AI could master domains requiring creativity, intuition, and long-term strategy, not just pattern matching, not just classification, real strategic thinking. After AlphaGo, the conversation changed. It wasn't, can AI do this anymore? It was, what can't AI do? This paper shifted the entire perception of what artificial intelligence could achieve.
2017. Google Brain researchers publish a paper with one of the best titles in AI history. Attention is all you need. Up until now, if you wanted to process sequences, text, audio, time series, you used recurrent neural networks. RNNs process sequences one step at a time, word by word, token by token. This is slow, and it makes parallelization impossible. Vaswani and his team said, throw away the recurrence, replace it with attention. The self-attention mechanism lets every word in a sentence directly interact with every other word all at once in parallel. This is the transformer architecture, and it's not an exaggeration to say this paper created the modern AI era. Why? Because transformers scale. You can train them on massive data sets with thousands of GPUs in parallel. RNNs couldn't do that. Transformers unlocked the scaling laws that gave us GPT, BERT, Claude, Gemini, every large language model. This paper has over 100,000 citations. It's one of the most influential papers in computer science history. And the architecture they described? It's basically unchanged in modern LLMs. They got it right the first time. 2018. Google researchers ask a question. What if we pre-train a language model on a massive amount of text and then fine-tune it for specific tasks? They introduce BERT, bidirectional encoder representations from transformers. And the key word here is bidirectional. Previous models read text left to right. BERT reads it in both directions simultaneously. It understands context from both sides of a word. Here's the magic. They trained BERT on two simple tasks. First, predict masked words. The cat sat on the blank. Second, predict if one sentence follows another. That's it. But by training on billions of words, BERT learns deep representations of language. Then you take that pre-trained model and fine-tune it on your task, sentiment analysis, question answering, whatever. And it achieves state-of-the-art results across 11 different NLP benchmarks. This is the ImageNet moment for NLP. After this paper, everyone adopted pre-training. Transfer learning became the standard. This paper proved you could build one model that understands language, then adapt it to thousands of tasks.
And now we arrive at the paper that started the current AI revolution. 2020, OpenAI publishes Language Models Are Few-Shot Learners, the GPT-3 paper. GPT-3 has 175 billion parameters. For context, BERT had 340 million. This is a 500x increase. And OpenAI discovered something profound. Scale changes everything. They showed that if you make a model big enough and train it on enough data, something magical happens. The model develops emergent abilities, abilities it was never explicitly trained for. You can show GPT-3 a few examples of a task in the prompt, few-shot learning, and it figures out what you want. Want it to write poetry? Show it 2 examples. Want it to write code? Show it 3 examples. Want it to answer questions? Just ask. No fine-tuning needed. The model is general purpose. This paper introduced the era of foundation models, models so capable they can be adapted to thousands of tasks just through prompting. This is why ChatGPT exists. This is why Claude exists. This paper proved that bigger isn't just better, bigger is different. And here we are today. Everything you interact with in AI traces back to this scaling insight. Before we wrap up, there's one more crucial piece of the puzzle: scaling laws. Both OpenAI and DeepMind published papers studying how model performance changes with scale. OpenAI's 2020 paper showed that performance improves predictably with model size, data size, and compute. Power laws, smooth, predictable curves. But DeepMind's 2022 Chinchilla paper added a critical insight. You need to scale both parameters and training data together. Their 70 billion parameter Chinchilla, trained on 1.4 trillion tokens, outperformed much larger models trained on less data. The lesson? It's not just bigger is better, it's bigger plus more data is better. For a fixed compute budget, a smaller model trained on way more data often wins. This research guides how companies train models today. Why does GPT-4 have both massive parameters and massive training data? Because of these scaling laws. These papers turned AI development from an art into a science. All right, what can you take away from this history? First, AI progress isn't magic. It's incremental. Each of these papers built on previous work. Transformers needed attention mechanisms. GPT-3 needed transformers. AlphaGo needed CNNs. Everything connects. Second, architecture matters as much as data. ResNet skip connections, transformers attention, GANs adversarial training. Clever design solves problems that brute force can't. Third, scale reveals new capabilities. We didn't know few-shot learning was possible until GPT-3. We didn't know emergent abilities existed until we built big enough models. Sometimes you have to build the thing to discover what it can do. For developers, study these architectures. They're not historical curiosities. They're active tools. CNNs for vision, transformers for sequences, GANs for generation. Pick the right tool for your problem. And for everyone, the next breakthrough is being written right now. Somewhere, a researcher is working on the paper that will define the next era. That's exciting. Let's recap the 10 papers that built modern AI. 1. Backpropagation, 1986. The engine of deep learning. 2. LLMs, 1998. Computer vision begins. 3. AlexNet, 2012. The deep learning revolution. 4. GANs, 2014. AI learns to create. 5. Seek-to-Seek, 2014. Neural machine translation. 6. ResNet, 2016. Training very deep networks. 7. AlphaGo, 2016. Strategic AI. 8. Transformers, 2017. Attention changes everything. 9. BERT, 2018. Pre-training for NLP. And 10. GPT-3, 2020. Scale unlocks emergence. 10 papers, 40 years of research, and we're living in the world they created. If you found this valuable, smash that like button, subscribe for more deep dives into AI research, and drop a comment. Which paper surprised you most? Which breakthrough do you think was most important? Let's discuss. Thanks for watching. I'll see you in the next one.